In this video, we're going to look at modeling exponential growth. In particular, we're going to use exponential functions to model population growth with a particular example of an animal population and bacteria in a culture. To model exponential growth, we're going to start with a standard exponential function, something like p of t equals p sub 0 times a to the t. This is an exponential because our variable t is in the exponent of our expression. P of t here will represent the population size at time t. And we're using the word population here to be very general. It can be the population of the number of bacteria in a culture. It can be the number of fish in a pond. It can be the number of people in a city, or many, many other things. So population is just sort of the group that is growing under our exponential model. P sub 0 stands for something very specific, and the notation sort of gives away what it might stand for. But if we weren't sure, we could always go ahead and compute this function at t equal to 0. And so p of 0 would equal p sub 0, whatever number that is, times a to the 0 power. And a to the 0 power is always going to be 1, because anything to the 0 power is 1. And so we just get p sub 0 times 1, which is p sub 0. So p sub 0 is going to be the population size at time 0. And so we'll call this our initial value. And so this will be the initial population size at the beginning when time is 0. And this number a here in this context is going to be called the growth rate. And in particular, it is going to be, for this context, when we have growth, it is going to be a number greater than 1. There are many different models to represent exponential growth depending on the context and what is known and what is being trying to be determined. This particular formula will work for any kind of exponential growth example, regardless of the context. And so in this video, we're going to simply use this model in all of our examples. Our first example concerns a fox population in a certain region. This fox population was estimated to be 850 in the year 2010. 5 years later, in 2015, the fox population was estimated to have grown to around 1,400. We're going to assume the population is growing exponentially, and therefore we can use an exponential function to model this population size at time t. And we're being asked to find two different things related to this population. First, we're being asked to find how many foxes there should be in the year 2021. And the second thing is how long it will take for the fox population to reach 5,000. So before we can answer either of these questions, we need to develop an exponential model that gives us our population at time t. One thing that will be important is to notice what t will represent here in this particular problem. Since we're starting our model here in the year 2010, we want 2010 to correspond to t equal to 0. So when we do make a model, we're going to want t to represent the number of years after 2010. And with that in mind, in part A here, when we want to know the number of foxes in 2021, we're going to want to use t equal to 11, because 2021 is 11 years after 2010. So let's take a look at the model that we can build to model this situation. We know our model is exponential, so we know it's going to have the form p of t equals p sub 0 times a to the t. We're given a couple pieces of information. We're told that p sub 0 is going to be 850. Remember here that t is the years since 2010. And so with this designation, p sub 0 will be the population in the year 2010, which was given to be 850. The other piece of information that we're given is that when t is equal to 5, and that would be in 2015, under our designation for t, we know that p of t, or p of 5, is going to equal 1,400, because there's 1,400 foxes after 5 years in 2015. Now, if we then substitute these numbers into our model, we're going to have, with t equal to 5 here, we're going to have p of 5 on one side, which is 1400, will equal p sub 0, 850, times a to the 5th power, because here t is 5. We're going to solve this equation then for a, and we'll have our growth rate. So if we divide by 850 on both sides, we obtain 1400 divided by 850 equals a to the 5th. We could certainly simplify 1400 over 850. However, at some point, we're going to just substitute this into a calculator, so it's fine to just leave it like this if you like. In order to solve for a, we're going to take each side of this equation to the 1/5 power. And so a is going to equal this number 1400 over 850 to the 1/5 power. And at this point, we can enter this into a calculator and see that this is approximately 1.1049. So this will be our growth rate for this particular exponential model. And so the model that we're going to use in this problem, in this example, is p of t equals 850 times 1.1049 raised to the t power. So this is the model that we'll use to answer both of our questions. Our first question asked us to find the population in 2021, or when t equals 11, because t is the years after 2010. In this case, we simply have to take our model and substitute 11 in for t. So we obtain 850 times 1.1049 raised to the 11th power. And using a calculator, this is approximately 2,546. Notice that we rounded this to the nearest whole number because we're looking for the number of foxes, and foxes should be counted as whole numbers. There are certainly some decimal places after the decimal point in this number, but we're not really sure how to interpret a decimal part of a fox, so we're going to always round to the nearest whole number when that makes sense. In part B, what we're being asked to find is want to find the value of t where p of t equals 5,000. So p of t represents the population after time t, and so we want to know when is that population equal to 5,000 foxes. And so we're going to substitute these values into our model. We have p of t equals 5,000. And that is equal to p sub 0, which we know is 850, times our growth rate, 1.1049 raised to the t. And we need to solve for the variable t. In order to do that, what we're going to do is first divide both sides by 850. If desired, you can simplify that fraction on the left side, although there's really no need to, because eventually we are going to just type this into a calculator. At this point, we have on the right-hand side an exponential term with our variable in the denominator. In order to deal with that appropriately, we're going to need to take a logarithm of both sides. We can use either natural log or common log. In this case, I'll use natural log, simply because it is less writing. So we'll have natural log of 5,000 over 850 equals the natural log of 1.1049 raised to the t power. And using a property of logarithms, we are able to take this exponent of t out front and multiply by t. And now our variable is outside of our exponent. When we do that, we get natural log of 5,000 over 850 equal to t times natural log of 1.1049. And now to solve for t, we can simply divide by the natural log of 1.1049. And so this is our exact value for t. And we can use a calculator here to approximate this value, and it looks to be about 17.76 years. So in this particular case, it will take almost 18 years for this fox population to reach 5,000 foxes. If we cared about the year, we do need to remember that t is the years after 2010, and so this would be 2027 when this would actually occur. For another example, let's say we have a bacteria culture that starts with 8,600 bacteria, and after 2 hours, the culture has 11,625 bacteria. We'd like to know how many bacteria there'll be after 7 hours, and we'd also like to determine the length of time it will take the number of bacteria to double. This is called the doubling time for the population. So the doubling time is simply the amount of time it takes for any population size to double. We'll solve this example very similarly to the previous one by building an exponential model that models the number of bacteria in the culture at time t, and then using that model to answer our two problems. So again, our goal is going to be to build an exponential model using our standard exponential form, p of t equals p sub 0 times a to the t. In this particular case, we're given that p sub 0 is going to be 8,600, the initial number of bacteria. And we're also told that after 2 hours, the number of bacteria will be 11,625. And so that will be the value of p of 2, the population after time t equals 2. If we substitute these values into our model, we obtain the equation 11,625 equals 8,600 times a squared. And we can solve this for a using the same algebra as in the previous example. We'll divide by 8,600. Again, this certainly simplifies, but because we'll be using a calculator later, there's no particular reason to do that now. That'll equal a squared, and then a will simply be the square root, or this number raised to the 1/2 power. And this, according to a calculator, is approximately 1.1626. So this will be our growth rate for this particular population. Putting this into our model, we see that the model for this bacteria culture is p of t equals 8,600 times 1.1626 to the t power. This is the model that we'll use to solve and answer both of the questions that were posed. The first question asked for the population after 7 hours. Using our exponential model, this is asking for the value of p of 7. So we simply replace t with 7 in our model. So we have 8,600 multiplied by 1.626 raised to the 7th power. And according to a calculator, this is approximately 24,689. Again, we're rounding this to the nearest whole number, as the question asked for the number of bacteria, and only whole number answers make sense for that particular type of question. In part B, we're being asked to find the doubling time. We want to know the time it takes for the population to double. So we want to know the value of t, where our population at size t is equal to 17,200. Now this number was not given to us in the problem. However, it's pretty easy to see that this is twice the initial amount. Right? The initial amount is 8,600, and if we double that, we obtain 17,200. So here we're looking for the time it takes for the population to go from 8,600 to 17,200. To do that, we simply use our model with p of t equals 17,200 substituted in. So we have 17,200 equals 8,600 times 1.1626 to the t. Algebraically, very similar to the previous problem. We're going to divide both sides by 8,600. And in this case, I actually am going to simplify because I know exactly what 17,200 divided by 8,600 would be. It's going to equal 2. Remember that 17,200 was developed by doubling 8,600. And so we're going to get exactly 2 over there. So this is a case where we would simplify because it's easy to do. We have the variable in the exponent. So again, we can take a logarithm. Again, I'll take a natural log here. So this will be natural log of 2 equals the natural log of 1.1626 to the t. Using log properties, we can bring that t down. So this will be t times the natural log of 1.1626. So dividing by the natural log of 1.1626, we see that t is going to be the natural log of 2 divided by the natural log of 1.1626. And according to a calculator, this is approximately 4.6 hours. So it will take this bacteria culture about little over 4.5 hours, 4.6 hours, in order to reach twice the initial amount of bacteria.